Most nights the sky looks calm, a scattering of stars, a faint haze where the Milky Way stretches across the darkness. Nothing about it suggests excess or abundance. And yet, every point of light belongs to a structure so vast that even the idea of counting similar structures elsewhere begins to strain intuition. From inside one galaxy, the universe feels sparse, empty even. Large distances dominate perception, not numbers. But as telescopes improved and surveys deepened, that sense of emptiness began to dissolve. Faint smudges multiplied. Deep images revealed thousands of galaxies where none had been visible before, and slowly a quiet problem emerged. How many galaxies are actually out there? Not how many stars, not how big the universe is in theory. But how many separate, gravitationally bound systems of stars exist within the part of the universe that can, in principle, be observed? A question that sounds simple, almost innocent, yet refuses to settle on a single number. Every attempt to answer it runs into limits of light, limits of distance, limits of definition. The further outward observations reach, the more galaxies appear, often smaller, fainter, and easier to miss. And beyond a certain point, even existence itself becomes something that must be inferred rather than seen. This video is not about rushing toward a final figure. It's about how astronomers approach the problem at all, how nearby galaxies inform distant ones, how surveys, deep fields, and simulations slowly build a picture that is always provisional, and why the universe seems content to reveal structure without ever offering completion. Welcome to the Sleepy Scientist. If this kind of slow, thoughtful exploration helps you unwind, consider liking the video and subscribing to the channel. And while you're settling in, let me know where you're watching or listening from. From inside a city under a dark sky, or somewhere in between. There's only one galaxy that can be experienced from the inside. Every other galaxy appears as a distant object, a patch of light against darkness, but this one surrounds the observer completely. Stars appear in every direction. Dust lanes stretch across the sky. A faint band of light arcs overhead on clear nights, marking the dense disk of the Milky Way seen from within. This embedded position feels intimate, even familiar, yet it quietly distorts perception in ways that are easy to overlook. From the inside, symmetry is difficult to judge, scale is hard to measure, completeness is almost impossible to assess. There is no external vantage point from which the full structure can be seen at once. Instead, the Milky Way must be reconstructed indirectly, star by star, region by region, using distance estimates, motion, and brightness as imperfect guides. That challenge shaped the earliest attempts to understand what kind of galaxy this actually is. At the beginning of the 20th century, astronomers attempted to map the Milky Way by counting stars in different directions. One of the most influential efforts came from Jacobus Kapteyn, who assembled one of the first systematic models of the galaxy using star counts and assumed brightness distributions. His model suggested a modest flattened system with the Sun located near its centre. It was elegant, mathematical, and deeply wrong. The error was not carelessness, it was invisibility. Interstellar dust absorbs and scatters light, especially in the plane of the galaxy where stars are most densely packed. Distant stars appeared dimmer not because they were few, but because their light was being quietly erased along the way. Kapteyn had no way to account for this properly. As a result, the Milky Way appeared smaller, neater, and more complete than it actually is. This early mistake matters because it reveals a deeper pattern. When observation depends on light alone, absence can masquerade as emptiness. What is not seen may still exist in large numbers. That lesson echoes through every later attempt to count galaxies beyond the Milky Way. As techniques improved, astronomers began to look not only at where stars were, but how they moved. Stellar motions offered a different kind of information, one less dependent on brightness alone. By tracking how fast stars orbited the galactic centre at different distances, it became possible to infer how much mass the galaxy contained and how that mass was distributed. This is where rotation curves enter the story. When orbital speed is plotted against distance from the centre of a galaxy, classical physics predict a steady decline beyond the region containing most of the visible matter. Instead, observations showed something unexpected. Stars far from the centre were moving just as fast as those closer in. The galaxy behaved as though it contained far more mass than could be seen. Vera Rubin